Hello, good evening. This is Professor Khan, and we are covering in this week uh, the introduction for EST-205. So this is first, the first class, and I'm gonna try to see. Okay, I can write. That's fantastic. Okay, so we'll do an introduction for this course, which basically is going to be a recap for the stuff we studied in EST-204 heat system design. So this course is advanced heating system design, where we will talk about different kind of systems, how do we use them, how they are different from one system to another, and I will walk you through it little by little. And for the book, you will use my book, which is residential heating, and I put that in Blackboard as well. So let's start. I'll give you some introduction. I'll try to ease you into it. Most of this information should be a repetition and something we already did before. Okay, so moving on. Erase. Okay, how about this now? Okay, so first off, let me just make sure that everything's all right. Okay, first off, again, heating coming into a house was done firstly by having a wood stove or burning stuff inside the house, and then in the beginning of in the late 18th century, beginning of the 19th century, we started to have steam as the steaming power. We started moving engines and having the steam trains, and we use that as actually as the vacuum pump. So we got the idea of heating a house using steam as an enclosed system. The first type of heating was just pumping steam into the space, and that was not very productive because, as you can see here, I was asking you what do you think would be the problem, and the problem with that would be that the place will be very soggy. Even though in the winter you will have a lot of dryness, so the steam seems to be productive, but it was not very, very common to have steam in a loop. It was completely just pumping steam into the room. And if you think about it, it was a progression from having a wood stove or a fireplace. Usually people leave a pot of water on the stove to heat the place faster. So the steam will enable the heat to disperse faster inside the vicinity. But again, it's really difficult to control and you can overdo it, and it uh, can lead to a problem of sogginess inside the house. But that was the beginning, and it was going on for a while. When the place gets a little bit damp, probably they will close. Well, they will turn off the fire, take off the pot out of the fire, then open a window. Steam inside tube did not come until the 1820. That was the beginning of a closed system into pipe and having what they call now the mattress, which is the radiator. So again, fire inside a dwelling or a house came with fireplace, then a wood stove, pumping steam inside the room, and then finally, uh, I mean, as a closed system came that steam inside tubes and radiators. Okay, let me move on from this slide. So American inventor Stephen Gould in 1845 introduced the self-regulating boiler and the practical radiator design, which is called the mattress. It's called the mattress because it looks like a sleeping mattress. It's have sections in it, and you can add section to it. Probably that's from the 1845, and that system, if you live in Western Mass, you will see a lot of houses still use steam power. That system was very efficient. It did the job. I mean, for its time, it was very efficient. It did the job very well, and it's still being utilized till this day. And chances are you will be working on it at some point, not for new installation, but for old system that has already been installed. So Stevenson, Sam improved in the system and the concept and started his company HB Smith, and this is actually here in Massachusetts. So we kind of located in the birthplace of steam for residential. HB Smith is still in business since that time. So why did we start with steam and not hot water? I'll give you a second to think about that. So steam moves by itself from high pressure to low pressure, and at that time the pump has not been introduced into the market yet, or the practical pump. So it was really difficult to move hot water. Moving steam was very easy. Steam rises with just like hot air. So all you need is a pipe and steam to go through it. So that's why we had steam and not power and not water. And now we have water system. Hot water system is more common than steam because we can transfer water with ease without a lot of cost. So the introduction of the pump came in the 20th century. So that's a little bit kind of recent, relatively speaking. And water was used in heating system, and it's the system called hydronic system. Hydronic, it means it uses water. So steam is hydronic and water is also hydronic. There's a lot of debate which one is called hydronic. I've seen them used interchangeably. So you can say steam hydronic or water is hydronic. Electrical controls were added to the system later on, meaning the low water cutoff, auto feeders, what else? Controls, thermostat, etc. But the system has been there, sometimes using coal, sometimes using just primitive primitive equipment with not a lot of control, and they have been improved upon ever since. So probably you will go into a system where you will see a lot of retrofitting happened. You will see a boiler with coal that has been converted into oil, then has been converted again into gas. So it is very possible. Piping took advances. Again, you'll see some advances when it comes to piping in hydronic or heat system. I think it's very marvelous how we can follow up the progress of heating system inside a house to have the comfort and convenient that we have now, and we should not take it for granted. There were times where you have to chop your own wood to heat the house. Now we just click a button and the house get controlled to temperature that we need. So piping did advance a lot. If you look at the steam system, piping was very elaborate, was very heavy, was very much involved and cost a lot of money. So it wasn't for everybody to put heat in the house. So piping took a lot of advances from steel to galvanized steel to PEX to PVC and different kind of pipes. Radiators have changed a lot again, from the steam mattress radiators to the baseboard radiators to the kickboards to a lot of panel that you can hang on the wall as well. So, and again, these things are an ongoing area of research. So there's a lot of area to improve and come up with new ideas and new means to heat space. Uh, okay, so we talked about some kind of evolution for heating a building, and so far from what I can recall, we can heat a house using electricity, but so far using electrical coil to heat a house is very expensive. We talked about that in the other course. Uh, it is efficient, but it is expensive. We said that 1 BTU equal 3.4 watts, and I'll show the conversion here. We'll talk about that as well. So when it gets really cold, so far we still need to burn something for heat, and mostly it's going to be hydrocarbon or carbon-based material. So let's talk about BTUs. So the BTUs we get from, I want to remind you that 1 BTU is the energy stored in one matchstick, okay? And it's also the energy required to raise 1 pound of water by 1 degree Fahrenheit. So it's really small. BTU is very little. So for coal, again, depends on what kind of coal, you get 55,000 BTU per pound. Some problems with coal, I mean, we had that for a long time, is shutting down is an issue, regulating is an issue. You cannot having high and low. And I give an example here of comparing propane grill versus charcoal. With propane, you have more control. With charcoal, you have to, it's a little bit more elaborate. You need more experience to control the fire to grill with charcoal. So same thing with coal. You hardly ever see houses being heated by coal now, even big building. Startup is also an issue. It does not ignite as fast as oil or gas. Cycle is not feasible, and there's a lot of waste of fuel. Uh, Turning it on and off is very difficult, so you end up turning it on and leaving it on, and whatever excess heat you have, you just dump it outside. So remember, when you look at the old movies and you see a lot of steam coming out of big cities, that is waste. Whenever you see steam coming out, that is waste. That means we are just leaving the boiler on, and whatever heat we don't need inside the house, we just dump it outside. And I also heard that a lot of big boilers, buildings now, they turn the heat on all winter and they open the windows. That is completely waste of fuel, waste of energy. And I think in some places it's against the law. So fuel oil, which is diesel oil, which is also similar to biodiesel, they're all around 130 to 140,000 BTUs per gallon. 1 gallon is 7.5 pounds, and that will give us 18,000 BTU per pound. So if you want to compare both coal and oil, you'll see the comparison here that it's coal still very dominant when it comes to the BTU per pound per weight. Coal is still king. Okay, and moving on. Wood pellets, 8,500 BTU per pound. Natural gas, around 20,000 BTU per gallon. Weight is going to be a little bit difficult to understand, and to convert natural gas into gallon, you have to depressurize it and so on. I'm just trying to give you an idea of the amount of fuel and BTUs per weight or size. What about electrical heaters? So probably you're hearing some banging on my video here, and that is my steam now. I just turned on the heat, and you can see the pipes are expanding and doing this clicking noise. So I have steam heat in my house here, and you can hear it clicking. I hope it's not overwhelming. So, okay, what about electrical heaters? They use 3,400 BTUs for kilowatt hour. That seems a little bit decent sometimes, but if you think about how many BTUs do you need, it's a lot. And a kilowatt is around 10 to 15 cents per kilowatt, which is expensive. So if you keep that running all day, you will have a little bit of higher bill. Okay. All right. Okay, moving on. Boiler design. So some information about boilers and boiler designs. So we have came to conclusion that eventually you will need to have some kind of fuel to keep your house warm. You cannot rely on mini splits or any other components right now, especially in New England when it's really cold. So what you will need to do at some point is have a boiler. Boilers and boiler designs. Who designed boilers? This is the ASME, the American Society of Mechanical Engineers. They do the design and they approve the boiler. It takes a lot of engineering to go through the design and make the walls needed for that. And moving on. Again, they have improved a lot throughout the years. The design have changed. They became smaller, more safety features, and they became more reliable and more affordable. Um, there was an accelerated improvement in the 1980s. They became more efficient, and they have implementation of energy and air quality standards. Okay, what else? So we did talk about the oil prices were high, and they also installed the Clean Air and Clear Water Act. So we're more aware about the smog and the pollutant and what are we uh, burning to make heat. So there was a lot of improvement on the efficiency of boilers. So if you have a boiler that has been installed in the 80s, probably it's more efficient than one that's been there since the 50s or 60s. And chances are that they are still there, installed and still running in a lot of houses. So again, now they're made out of stainless steel, cast aluminum, and different kind of sheathing and insulation. They're more efficient. They have different or higher combustion efficiency and also thermal efficiency, which is how much heat is being absorbed by the boiler itself. Electronic controls were added, automation and automatic ignition, fuel regulation, and lower cost of running, and they keep improving. The best so far boilers we know of is the gas boiler that are condensating boilers. Condensating boilers actually absorb all the heat that has been made by burning the fuel, mainly gas, and basically rejecting heat out of the flue pipe at 60 or 70 degrees Fahrenheit. So that's really great because we're absorbing all the heat we did by combustion and making them have a thermal efficiency of at least 95. That is huge. For non-combustion boiler, you get an efficiency of 75 to 80 if you're lucky in terms of thermal efficiency. Thermal efficiency is how much heat we absorb by the boiler than the heat that we actually ejecting into the atmosphere. So the U.S. Department of Energy and the American Society for Heating, Refrigeration, and Air Conditioning Engineers, actually, they set the standards for boiler efficiency. What is the low end, what is the high end, and what is acceptable and what is not. So all these organizations has to agree together into a standard that we should put on the boiler. And again, as usual, some older boiler that's still running and people has invested in them are still grandfathered in, but for new stuff, you have to try to get the latest and more efficient. And as of the last few years, things has really jumped and took a leap into efficiency, and we're trying to reduce the amount of heat we use by burning stuff. But again, for now and for the near foreseeable future, we're still going to be burning fuel for heat in New England and areas that extremely cold. In terms of heat pump, we can manage to have heat using mini splits and heat pumps for states that are south of DC. Once the temperature drops below 10, we are kind of hopeless and we need to burn something for heat for the time being. There are some ideas and alternatives using biofuel or using electrical coils with energy that has been stored using solar or wind turbines, but that's not going to happen for the next 10 or 15 years. Um, the American National Standards Institute, ANSI, they provide the standards and regulate testing methods for those boilers and what test is required to deem the boiler usable or not usable, and the material has to be according to their standards. Local fire departments have to approve the installation, and the fire marshal has to approve the installation. So the once you install a new boiler, you have to go and apply for a permit. The fire department will come. The fire marshal will have to stamp and approve. Of course, it's not going to come personally to every installation. They have delegates, but the fire marshal has to approve that this installation is up to code, and every town has its own code, so you have to pay attention to that. Okay. Combustion, as we said, we are just to give you that's something we went over last semester, but we want to go over it a little bit more, which is combustion for heat. Again, that's something you have to do. It is important for you to remember and understand what is happening inside the boiler. So if we look at that, hold on, let me get the okay. Let me see if I got everything. Okay, I'm gonna go back and I'm gonna do some notes here. So if you look at the composition of air is 21 oxygen and 79 nitrogen. Some people say 20 and 80, but mostly we have oxygen is mostly we have nitrogen and 20% is oxygen. So when we burn fuel, like why do we need the right mixture? We need the right mixture because we need to burn all the fuel. And I said, think of the fire grill and think of candle. Whenever you have smoke, you know you have incomplete combustion. Focus on that. If you have smoke, you have incomplete combustion, which means you did not burn the fuel completely and you have excess fuel. And that is something that you don't want. So there is primary air and secondary air. What does that mean? Primary is the air that comes in with the fuel. So for any fuel that we burn, we will use fuel. This is fuel, hydrocarbon, which is hydrogen carbon. This is the fuel, which is fossil fuel. It's gonna be oil, gas, coal. They all have the same chains of carbon and hydrogen. This is the oxygen coming from air, nitrogen coming from air. So both those are air, and the spark is what we use to heat to make to start the fire. So once we have this mixture together, we'll have heat, CO2, water, nitrogen comes out because we do not burn nitrogen, and those two things that we do not like, which is sulfur oxide and nitrogen oxide. Where did the sulfur come from? It's a byproduct of fuel. A lot of fossil fuel have sulfur in them in a small amount, and as a result of there's no way around it, but we try to have low sulfur oxide and nitrogen oxide. So when you have the right amount of fuel to air ratio, you'll burn the fuel completely, and you do not turn up with any fuel in here. If you have any fuel, that means you have smoke, and that means you have incomplete combustion. This is referred to figure in the book. You can look at it later. It's for draft design, and basically to be able to extract all the fuel and combustion air coming from the combustion chamber to the outside. So again, we said we need to have the right amount of combustion air. We pre-mix air with the fuel before we ignite it. So we have pre-mix air, nozzle, and atomization of the fuel to have the small little combination of fuel and air, and we ignite them with the spark to be able to have the right combustion of air. And we did go over that in theory and control and in Energy System Lab 1, where we were introduced to the nozzle design and the point of atomization and why do we need the right mixture. So what I'm trying to say here is when you think of combustion inside the house, you need to know that you have to have the right amount of air to fuel to have complete combustion without smoke. All right, moving on. So we burn the fuel inside the boiler, we heated the water or steam. How do we transfer that heat into the house? So we did talk about this before, that heat transfer from one place to another, either using conduction, which is heat transfer through direct contact with material, or convection, which is heat transfer through fluid, either natural convection, which is the idea that hot air or hot liquid rises based on density and it's buoyancy driven, or forced convection, where you have to use a fan or a pump to move the fluid faster from one area to another. The other mean is radiation. It's infrared electromagnetic waves produced by heat. When you heat something to long period of time, if you heat something with high temperature, you will have electromagnetic wave coming out of it, and they transfer as heat. And this is the infrared heat. If you have a light, like the old light, like the incandescent light, if you turn it on, it will glow, and when it glows, it does produce infrared heat, and that is radiation coming as heat. And there is some kind of radiation that comes as light, and so on. LED light is mostly visible light and not heat. And I think I have a chart here that will explain that a little bit more. I like to refer to it. Yeah. So we look at any kind of radiation, any kind of wave. And if you look at this portion here, let me use my pencil. If you look at this portion here, when we think of radiation, this is infrared, which is waves of radiation that transfer into heat, and this is what we see as light, and this is what comes out as ultraviolet, which is some form of light that we don't see, but it's not useful for our purposes. It does not give us heat or visible light. So infrared is the form where we can get heat out. What about microwave? Microwave comes somewhere around here, and that's what we use for machines like the microwave we use at home, which transfer some waves that will heat food. And some lights do transfer heat through infrared. So at least we get to distinguish between visible light and infrared. And there are some ways to heat the house using infrared and radiation, and this is radiant floor heating. And there's panels that actually radiate heat, and instead of convection, it's not heating the air, it's heating you. And the best way to think of those types of heat is when you look at the food, uh, the light, when they put the food in the fast food restaurant into light, that light actually giving you infrared, so it does heat the food and not the air. So that's radiation heat. Or when you buy those little um, uh, dish-like heaters for home for space heating, and it just glows very hot and radiate heat into the surface. Okay, I hope that makes sense a little bit. All right, I'll move on. Uh, Now I'm trying to kind of refresh your memory about how to do heat loss and heat loss calculation, and we did that. I'm sure you know it by now. And we said Q equals area times U times delta T. And this is just a quick example to remind you of how do we do this calculation. And this here is the area. In this case, this is 12 because we multiply 3 by 4. And the wall is 3 inches thick. And I gave you an R value of 0.15 per inch thickness, just to refresh your memory how to use these values. So we have 0.15 times 3 because we have, I'm trying to calculate the R, and that's going to be 0.45 R value total per inch thickness, and the wall is 3 inches thick. And then we added 2 inches of fiberglass with R 3.2, I think, for both 2 inches. So another R, that's equal 3.5. So we have, if we added those two together, the R value will be 0.45 plus 3.5. That's 3.95 total, our total. And I'm trying to calculate, okay, so this is our value. What is U? U equal 1 over 3.95. So that will give me, if I get the calculation here for that, U, so I have 12 here plus 0.25, and this is the result of 1 over 3.95. And times delta T is 72 minus 35, 37. So what would be the total for this? 37 times 0.25 times 12, we get, so I have 111 BTU per hour. I know it's kind of messy, but if you follow through, you'll get that number over here. That's just a refresher of multi-layer wall. Another example. This example is to show you how to calculate insulation based on the heat transfer rate that you want. So in a way, you're trying to calculate reverse calculate how much insulation you need to reduce the heat loss. So remember when we said Q, let me go back. Trying to get my pen out, hold on. Okay, here. I'll try to do that. So Q equals area times U times delta T. Okay? If I want to solve for delta T, for U, U will equal Q over area times delta T. Okay, if I want to solve for R, U equal 1 over R. So Q will equal again delta T A times delta T. This is okay. So I'm just trying to manipulate the equation a little bit. And if that will lead me to have U equals Q over 1 area times delta T. And if I erase this, hold on, 1 over R equal Q over A times delta T. And if I want to solve for R, that will be R equal area times delta T. This is A here, and over Q. So I just flipped each one of them. So now I solve for the resistance that I require. And if I want to, but we know that R total usually is the sum of R wall plus R insulation. So I'm going to erase that. No, I'll just add it here. So R wall plus R insulation equal area times delta T over Q. And if I make it a little bit cleaner here, this will be, hopefully I have the equation here. Yeah, this will be the equation that you need to calculate for the insulation. So why do I need that for? So let's say, for example, you did the heat loss for a wall and you find that wall is losing 4,000 BTUs and you want to reduce that to 2,000. So you'll substitute to 2,000 here. You keep the area the same, of course. Delta T is going to be the same, and you subtract. You do this math over here, and you subtract the resistance of the wall, and that will give you the resistance insulation that you need to add to the wall to get to that number. So I will do an example and I will post it to show you how to do that insulation by itself on Blackboard. I think it will be very beneficial and it will be a good idea to see that. So I'll post an example for you. But keep that in mind because it's going to be something that's very useful for you when you go to do some house insulation and building. So outside convection, so keep that in mind. We'll move on to also convection, which is wind. It does also affect it does affect your heat loss. So we talked about conduction, convection, and radiation. Something also you have to think about that wind does affect your insulation, and it does also affect your forced convection. And that's something also you have to think about when it comes to heat loss. It's not always about resistance, but also about the convection outside the wall. In this slide, I just want to show you the boiler anatomy because we're going to be using a boiler at some point, and the flow of fluids. And in here, you'll see in this area where you're going to introduce your, this looks like a gas burner, where you will introduce your gas with your air coming in, and that's the primary air, and there's some secondary air coming sometimes from a swinging door in here and sometimes from the draft, and the whole combustion will go through the draft to the chimney outside the house. And you have your controls usually here. This is a low water cutoff, and here's my burner control, and this is the burner assembly in here. I should just point out things in here. So this is your controls. This is also control, and the burner assembly is this one, and combustion chamber is here. What else? And I'll do the labeling again. Control, burner assembly, combustion chamber, heat. This is the heat exchanger is always here, so make sure you know where it is because this is where you're going to clean when you do the boiler cleaning. The vent is here, the piping for the hot water or steam. Fuel supply is going to come from here, and this is your air intake here. Okay, that was good. All right, moving on. Sizing a boiler. It is very important to size the boiler, and you do that once you do the heat loss for each room. It does reduce the cycling, which wastes energy. And again, we did talk about oversizing a house and trying to open the windows or have it running without calculating the heat or without like using the heat. That's not a good thing. And you'll if you do that throughout the season you will lose a lot of heat and eventually uh, it will affect your fuel bill. Knowing the load requirement based on building heat loss, BTU lost has to be less than the BTU of the boiler, not but BTU of the boiler. So what does that mean here? That means that the BTU you lose throughout the building has to be less than what the boiler can generate. The boiler should keep generating heat, but the BTU that you lose through every hour should be less than what the boiler can supply because the supply of the boiler has to bring up the building from very low temperature and then maintain that temperature. So it's intuitive that you have to have a boiler that can supply more heat than the building is losing per hour. The boiler is not the entire system. That's something you have to think about. There are pipes, valves, connections, and so on, and it's very important to keep that in mind. Water versus air. Uh, what I'm trying to say here is having a boiler or a hydronic system is not the same as having forced hot air. They have different anatomy and different components and different strategies. So when you compare, you have to have really good comparison when it comes to cost and efficiency. How to dispense heat or disperse heat is a combination between water and air. What does that mean? Uh, let's think about in a room or a living space, you have a lot of air, and you are delivering the heat from the boiler to that place either by steam or water. And at some point, there's an interaction between the air and that water. And the water will stay in the radiator, but the air has to be heated. So the air has to interact with a radiation system or fins. So it's something to think about. How do you going to dispense that heat that you generated? You can use either a radiator, you can use radiated floor heating, you can use different kind of uh, equipment or tool or appliances to dispense that heat. So making the heat is not one thing. It's one thing, but dispensing that heat correctly is another uh, strategy. Again, I'm still comparing between uh, hydronic system and duct air and boiler versus furnaces. It's different strategy, and these are the most two dominant ways to heat houses in this area. So you have to always have that comparison, and sometimes it just boils down to personal preference than just efficiency. And when we say efficiency, it's very important to know what are we talking about in terms of money or in terms of energy or uh, capital cost or even maintenance. Okay, so that's what I have for you. Please watch the video that I'm going to post about how to calculate the resistance for the insulation needed for one wall. I'll do an example with me doing this calculation. Thank you so much, and please read the chapter 1 in the book. Okay, talk to you soon.